We're going to be solving another simple equilibrium problem. So we have our little cargo here, and from the problem statement we can see that this right here has a weight of 24 kilonewtons. Right? This comes from the problem here, and basically it gives us the geometry, and what it's asking for is determine the forces in the boom, which is this boom right here, and in the topping lift. So basically it wants us to find the forces here and here. Okay, so let's get started. Let's start by drawing our axis. We can start by drawing our free body diagram, actually. This is our B free body diagram for particle B. Let's start with the force of the boom. The little stick going this way. Let's call it force A. Force A here. Force A acting on this particle B. This is our B free FBD, free body diagram. So we have the force of A, which is this one right here. And then let's call it, let's move this here, F of A. And then we have the force of C, which is going this way, F of C. And we could put it here, F of C. And finally, we have the weight of the cargo, which is this one right here, weight of the cargo, weight of the cargo. F of A is this right here, and then weight of the cargo, which is 24, weight of the cargo, which is 24 kilonewtons because of the problem statement. So that's basically our free body diagram. And what we have to do now is just sum all the forces in the y direction and some of the forces in the x direction as well. So we got some of the forces in the y direction. That has to equal to 0. And some of the forces in the x direction. That has to equal to 0 as well. We don't have any moments in this case, so some of the forces of the moments about point B are also equal to 0. But in this case, we don't have any moments acting on at point B, so we can just get rid of it because we don't have any forces there. Okay, so let's get started with our equations. Okay, let's start with f of y. Some of the force in the y direction got to be equal to 0. Let's start with force of C, which is Fc. And then, okay, so we got to find the angle here real quick. We got to find the angle here, right? And the angle here. And so they give us the slope. Basically, they give us a slope of 4 in height. 4 in rise and 1 in height. This will give us the angle. So how do we find the angle of that? We have to do tan inverse. This we learned from trigonometry, but if you don't remember, it's a good idea to review. Tan inverse of rise over run, it's going to give you your theta. So that's how we find our theta here. Theta. So basically, when you put it in the calculator, the theta here, it's going to equal 14 degrees. So if we're looking at observing our force in the y direction, f of c sine 14 degrees, right? Now we got to sum of the forces in the FA, we call them, the forces from the rod. So plus FA, we call it sine. Let's try to find our angle here. Sine. So we know this is 90 degrees, right? 90 degrees. So then 40 minus 90, this is 50 degrees here. Do you guys see how 50 plus 40 equals 90? So that's how we know, that's how I know it's 50 degrees right there. Sine of 50 degrees. And then we have to include the force, the weight of the cargo, which is minus. Again, I'm putting minus because we know that the force of gravity goes down. And our convention is that positive is up. And then if we go down, then it's negative. So that's why our weight is negative in this case. So minus 24 kilonewtons. It's going to equal 0, right? That's the whole point of this equation, is that all of our forces in the y direction need to be equal to 0. Now we can find the forces in the x direction. Here. All right, we do the same thing. We look at the force from the cable, which is FC. We just call it RFFC in this case, FC. Cosine. Now we do the cosine because remember, now we're looking at the projection in the x direction, because this will give us the forces in the x direction plus the force from this from the rod, which we call it F of A, cosine of 50 degrees. And then our weight doesn't have any x component, so we can just say plus 0. Again, just because there's no x components from the weight. So now we have a system of 2 equations and 2 unknowns. So this basically becomes like an algebra problem. So we just gotta solve for that. I was working on this earlier, so I have the numbers, and I'm gonna help you guys go through it real quick. So basically, right here, sum of the forces in the y, it's gonna equal something like this: F of C times 0.241, this is a 4, 1, 2, plus F of A times negative 0.766 made a mistake. I don't know why I put negative here. This is just a positive, just a regular positive, 0.766. Because 50 degrees, sine of 50 degrees is 0.766. Yeah, times FA, it's going to give us our component, y component of this right here. Which is our y component and our x component, right? And y component. But basically, yeah, it's going to give us the y component and due to our force FA. And then all of this, if we simplify a little bit, it's going to equal to 24 kilonewtons, right? So if we add 24 here, it's going to cancel it, and then on the other side we just add the 24 kilonewtons. So that gives our first system of equations. Now we can go for some of the force in the x direction equation, and we can see F of C times cosine of 14 degrees. Cosine of 14 degrees is going to be cosine of 15 degrees. It's going to be 0.97. But we have to remember that our little arrow is pointing this way, right? So the projection is going to be along this direction. Do you guys see? This direction. So it's going opposite of our convention for the x direction, which is, okay, pretty much if you have something going up in the y, positive. You have something going up to the right, it's in the x direction, it's positive. But if it's going the other way, then it becomes negative. So that's why we write negative here, because it's negative of our in the x direction. Pretty much we have our point B here, right? And the projection is this way. So that means that the x projection, the vector, this one, FC, projection along the x direction is negative 0.97. That's why it's negative. And now we add plus FA. This one is 0.64. 0.64. And then all of this equal to 0. Okay, so now we have our equations of, we have our two equations and our two unknowns. So we can plug all this in. And after doing all, let's see, this math, we're going to get f of c. F of c equals to f of a minus f of a 0.64 divided by negative 0.97. And that's going to give us FA times 0.66, right? And now we have FC. Now we know what FC equals FC, right? So now we can plug it in to our other equation, to our sum of the y's equation. So it's going to be something like this. FA times 0.66. This, we're just plugging it in here. That's what we're doing. And then times 0.2412. And then plus FA 0.766. All of that's going to equal to 24. So once we solve for all this, we're going to get 0.02412 plus 0.766. FA times 0.93 equal to 24. And when we solve for FA, then we're going to equal 24 divided by 0.93 equals 25. Pretty much 25.8 kilonewtons. And then we could just use FA. So now that we have FA, we can just use any equation we like. We can use this one right here. And then we find that FC it's going to equal about 17 kilonewtons. FC is going to equal 17 kilonewtons. But remember that our answer isn't complete because we have to show what direction our forces are acting. Right now we just have the magnitudes, but it's important to find the direction as well. So since both of our answers are positive, you guys can tell here, positive is inherently so there's a positive. So both of our answers are positive, right? So what does that mean in terms of our answer of our results is that our directions we assumed in the beginning of our problem are correct. Okay. So this right here, I'm gonna move it down here. Body diagram BC. That means that our assumptions in the beginning for this free body diagram, FBD, were correct. You know, that means that, just so you guys know, I don't know if you guys know this, but when a force like this one, FA, that we have here, right? FA, I'm just copying it here. When it's pointing towards the B, towards our particle, it's considered to be in compression. FA. When it's pointing towards the object that we're talking about, it's considered to be in compression. And in this case, since the sign was positive, we're confirming the direction is correct. If they were negative, that would mean that it would look something like this, the opposite, right? The opposite of our assumption, which our assumption was this, and the opposite of our assumption is that it's pointing the other way. But since we have a positive result, that means our direction has been confirmed mathematically. So this is in fact the way of the force is acting. So that is a force of 25.8 kilonewtons in compression. So this is a force in compression. Uh, 25.8 kilonewtons, and we could call it compression. Again, the reason it's in compression, it's because it's acting. The direction of the force is towards our free body. That's why it's in compression. And then when we have another case like this one, like FC here, again we confirm the direction of the force because it was a positive result. That's how we know that our initial assumption was correct. This is called tension when it's pointing away from the free body. Do you guys see the difference? Away from the body, from the free body. That's considered tension. And then we could add this, which is the weight of our cargo. The weight of our cargo equal to 24 kilonewtons. And there you have it. That's how we find the reactions of due to the cargo in our cable and also in our resisting rod. So in the cable, we have force equal to 17 kilonewtons. In tension, right? So the force in the cable is in tension, and in the rod, this one right here, it's acting in compression. And that's what the results mean. So that's pretty much the problem. The problem asks us to determine the forces in the boom and the topping lift. And then here we go. We found both of the reactions here due to the weight. All right. I hope this video was helpful. Let me know what you guys think in the comments. And have a good day.